computer. There we go. Okay. So I did send an email about, specific inquiries, questions. I don't know if any of you have anything you want to actually that you wanted me to specifically address. I mean, is there anything, or if there isn't, that's fine. I have a list. All right, I guess I'll take the silence here. All right. Okay, so my list of topics then. All right, so one thing I want to mention, I get this question a few times. So when you start the session, so there are alignments that you can load, right? So this is in the SOP, right? Load the alignments, and then there's a gun alignment here, and then we'll use the TEM one here. So I got a question actually recently about, what if you're in the session, you have to take the holder out and change samples? Okay, do you have to do this? And the answer is no. Okay, so you only need to do the alignment loading and the FEG register at the beginning of the session. The only exception to that might be if you decided you wanted to do STEM instead of TEM, then you would need to load the STEM FEG register, but you don't need to load the alignment file again. So, you just do that at the start of the session, and you will be good to go. So you don't have to do that when you do a specimen exchange. All right, so I've got a couple of OmniProbe specimens on here. So we'll go ahead and find them. All right, so there's an empty grid. Okay, there's this guy right here. All right, so one thing I would like to point out, so this is a functionality that it's not in the SOP, but you do have the ability on this instrument, and I think pretty much any TEM, modern TEM, to actually store stage positions. Okay, so if you want to move quickly between, lamellas here, right? So there's a lamella here. You can come to the stage tab here in the stage panel and just click add, and that will store the position. Okay, this will remember, everything down here, X, Y, Z, alpha, beta. Obviously, we didn't set the eccentric height, or we didn't, tilt to align to a zone axis. So obviously we would probably want to do that, but this is quickly. So in other words, let's say that's one sample. Okay, and then here's another one. So now I believe right here, if you just click add, it just gives it like a number. But if you know the name of the sample, so I'm just going to call this lamella. And then if you hit return, oh, okay, so it actually renames it. Okay, so it renames the first one. All right, so if we click add, okay, so it adds this position. And then if we want to rename it, so we call it lamella 2, and then it will rename it. Even if you're not, so on something like this, obviously you only have 2 lamellas. It's not really difficult to kind of like lose things. If you're working on like particulate samples though, maybe for example, you have like an opening in a grid and you notice something interesting in one of those openings, right? And, maybe you want to come back to it later. Okay, you can store the position of it and then you can come back to it if you wanted to do something on it later. Okay, so that can be potentially useful depending on what it is you're after. So you do have the ability to store stage positions. One thing I also wanted to point out, when we do the eucentric adjustment, so we're not in LM mode when we do this, but eucentric is actually from a what's the right word here? From the most rigorous perspective, it's actually a mechanical position. So if I expand this stage panel here, okay, the actual eccentric position really doesn't have anything to do with the sample being in focus. The way that we set it normally is by being in SA mode, and then we push eccentric focus, and then we adjust the height to get the image in focus. But what we're doing in that instance is we're actually putting the lens, objective lens, at a specific preset value that corresponds to where the image would be in focus if the sample is at the right height. Okay, so to actually find eccentric, though, rigorously, we have to wobble the alpha tilt. Okay, so if you expand this stage panel, you come down here to alpha wobbler. Let's bump this up a little more to maybe 10 degrees and click wobbler. Okay, so you're seeing the image wobble back and forth. So the alpha axis is basically vertical here in the screen, along the screen direction. And basically, if you're at the right height, you're not going to see the sample move very much. Okay, so we're pretty close here. I mean, if I throw this off so you can see, right? So, I mean, obviously that's off a lot more. The reason I bring this up is sometimes the focusing method, this isn't an SOP, obviously. And, you know, for full disclaimer, everything that we're covering today, feel free to try on your own. This is not something you need my permission to try. It's not damaging to the equipment, obviously, but something I wanted to, you know, just point out. But sometimes other people have an easier time doing the tilt method than the focus method. Is there a question?
Yeah. So what were you were changing your alpha and beta tilts for eccentric focus
No, I
while
didn't
doing
change no, I didn't change anything with the beta tilt.
uh
Okay, all I
what
did was you come down here
mhm.
to alpha wobbler. Okay, so that's another good point. So eccentric is only relative to the alpha tilt axis. It's not relative to the beta tilt. Right? So again, you're not doing anything with beta. You're just, you know, you're turning this on and then it's going back and forth, right? So you can see it's basically not moving. We're pretty close right here.
So if it moves too much, what should we change? Is it just the value for alpha?
No, you're
Basic.
trying, okay, so if the sample's moving, okay, so now it's moving. So what you're trying to do now is you're adjusting the Z-axis buttons.
Okay.
Okay, just like when you do it in SA mode, you're using the Z-axis buttons to get it in focus, right? So same thing here, you're using Z-axis to minimize the movement. Okay.
Thank you.
So we can, sure. So we can actually, we can see how close this is when we actually go into SA mode. There's always going to be a little bit of a hysteresis. So, I mean, realistically, eucentricity, which is probably a word I just made up, is accurate to probably, if you know, if you do it correctly, to plus or minus a micron, I would say. Okay, but now we're in SA mode. Okay, so if I push eccentric focus, switch to, all right, so we're pretty close here. So if I move the Z button, right, so you can see I have a lot more contrast. This sample, by the way, so this is a, it's a photonic device that is based on indium phosphide. So we haven't actually, it's actually this thing here in the middle, which will show you a little bit more. But anyways, it's based on a single crystal of indium phosphide. But yeah, these single crystals are great. They show a lot of contrast. But yeah, so we were actually pretty close just with the alpha adjustment. And again, you should be, provided that the person who sets the microscope up, you know, sets eccentric focus properly. All right, so that was the alpha tilt. I'm just gonna go back and forth here between my list here, storing stage positions. Okay. Okay. All right. I had a question. Someone actually sent me a text message yesterday evening. I don't know if that person's on the meeting now or not, but he wanted to know about beam current, if there was a way to measure the beam current. And yes, the answer is there is a way to measure it. So down here, you can see where it says screen, okay? So what you want to do here is make sure that the entirety of your beam is inside of the flue screen or the flue cam, okay? Obviously, you don't want something like this, right? You put it like that, and whatever you're reading here, that is your beam current, okay? It doesn't really matter what your mag is, right? I mean, you're changing the size if you change the mag, okay? So if I do something like this, okay, you can see I still have, more or less the same number. I think there's going to be like a little bit of variation with this, but it's not.
Hi, Nick.
Yes.
Yeah, just a question. So will the beam current change a lot at a different magnification? Like if I mean like a very high, like 100K versus
Well, let's
like
take a look and see, right? So, I mean, we're hanging out around 1.7 nanoamps here. Okay, so I mean, if we go, it shouldn't, but let's take a look here and see. So, yeah, we're still pretty close.
I see. So basically at a higher magnification, the beam is more condensed and then it's a higher density, right?
Right, so you're not changing the current. Now
I see.
the caveat I would also say is you want to do this in vacuum. You don't want to do this over the sample if you can.
Oh, okay, gotcha. Thank you.
Sure. Now, as far as measuring the size of the beam, that is also pretty straightforward. So the way to do it would actually be, so normally we don't actually, we would never actually use this kind of a geometry when we image the sample, right? So we would actually expand the beam kind of outside the view field here, okay? So, and what we don't want to do either when we actually acquire the, when we put the beam on the SATA camera is we don't want the beam inside of the viewable area because it's, potentially injurious to the beam, right? So if we just expand it so it's outside the corners, okay, so you can see my radius or diameter is basically just outside the corners. Okay, so if I go now to the acquisition window, okay, so, and now down here, okay, I have the field of view right now. Okay, so that's from left to right here. Okay, so obviously from here to here, right, that's √2 times this number. Okay, so, and we know because the viewable area is basically, the same, right? So as what you see on the flue cam. Okay, so if you multiply this number by √2, that gives you a diameter approximately for the beam. And then based on that, you could calculate a beam diameter and then a beam, then a current density as well. Okay. Something else to point out, this guy right here. So some of you have kind of seen maybe two variations of this with the images. So there's what's called a data bar and there's what's called just a scale bar. If you right click, and you have to do, you can do this in either acquisition or in processing, it doesn't matter, okay? But if you right click here, you can see you have an option here for scale bar or data bar, okay? So scale bar just puts, scale bar in the corner. The data bar doesn't put anything on the image, it puts a bar underneath it. I actually prefer this now over the scale bar personally. The reason for that is you get a little bit more info with the data bar, but you also no longer have the scale bar directly on the image. So it's very easy to just crop this out, because when you actually export this as a TIFF, you have this underneath it, but then you can just crop it. And then if you want to draw in your own scale bar, you can for like a publication or whatnot, but you also get this additional info that you didn't have before. Let me pause this for a second. And that there's another thing actually, let me go back here to acquisition and let me blank the beam because that's good practice. While we're not actually using it, we want to blank the beam off. I'm going to open up here. An image that one of these images I took yesterday. Okay. Let me open up a better one here. Open up a few of them. Okay. All right. So when you acquire these images, one thing you need to understand is that as you're seeing them here in Velox is actually not what you end up getting when you export them. Okay. And it's a very subtle difference, but it actually, if you scrutinize it carefully, you can kind of see it. Okay. So, and what I'm talking about is what's called interpolation. So if you scroll in really, really far, right? So we can kind of like see the individual pixels, okay? Right click on the image. There's this thing here called interpolation. Okay, so this is a digital processing that's done to the image. And you can think of it almost as like a smoothing effect, okay? And so this is on by default when you acquire the images and you're viewing them in processing or you're viewing them in acquisition. Okay, so if I turn this off, okay, so I don't know if you can see that. Here, let me scroll in a little more. Okay, interpolation. Oops. Okay, there we go. Was it mag sensitive? Yeah, I think if you, okay, yes, if you mag in too far, you don't see it. So right about here, if you look at it now, okay, it kind of smooths it out a little bit. Okay, so anyways, that's called interpolation. So it's basically like a smoothing effect that it has on the images when you get them. So what the point though is, okay, it's not actually, if I turn this off, okay, if we look at this image, let me see which one I have here. 5, that's not the one I have. Oh, this one, there we go. Okay, 11. So if I find the TIFF, I want to find the TIFF that I exported. Okay, so if we scroll in here, okay, on the TIFF doesn't actually have that. Okay, can everybody, hopefully you can see the difference here. So let me actually get this at a comparable scale here so we can kind of. Okay, so this is the exported. This is no interpolation. This is interpolation on. Okay, so I think hopefully you can see the difference there. So the one that you're seeing in Velox has interpolation on, and you don't see this in the exported image. Okay, so just something to kind of keep in mind. And really, until you kind of blow this up, you don't really see it. But I mean, I kind of have an eye for these things because I've just done this for so long. But if you've ever noticed that your exported images maybe just look a little bit different than how you saw them in Velox, that's probably what you're seeing. You're probably seeing the effect of that interpolation being on there. So, all right, let me go back to my list here. I'm gonna check these off here so I don't do them again. Got that one. Interpolation. Measuring beam current. Data bar versus scale bar. Okay, there we go. All right, so let's go back here to acquisition, unblank the beam, and then let's go and find the sample. All right. All right, so really quickly here, I'm gonna check my C2 aperture centering. Looks pretty good. That's another thing to point out. So like, what kind of so if you do sample exchange, what alignments do you need to redo when you do the sample exchange? I mean, really, when you get good at this, it's not really that hard to run through the full alignment again when you do a sample exchange. And really, that's probably what you should be doing. If you don't mess with something like the C2 aperture position, then that should still be, basically good. And you could kind of skip doing that. Things like astigmatism and rotation centering and the pivot points, those really you kind of need to do every time you do a sample exchange anyway. But I'm just checking this here. It looks good. I mean, the beam looks circular, so I mean, that's fine. All right, so this is a single crystal here. Let me go ahead. Well, actually, we didn't do the rotation center yet, so which is what I wanted to get to next here. All right, so what you're seeing here. So let me move this over. Okay. Right here, this interface, this here is electron beam assisted platinum deposition from the fib, and then this is actually the semiconducting material, so the indium phosphide. This is actually a damage layer on the surface right here, but this is all indium phosphide underneath, okay? So right now what I'm going to do is use my focus knob and focus, get minimum contrast, and then go to direct alignments, okay? And then we'll do the pivot points. What you're doing when you do these beam tilt pivot points is you're establishing what's called tilt purity. And that is a fancy way of saying that when the beam is tilted, it doesn't change its position. Okay, so that's the X pivot point, that's the Y pivot point. Okay, so now if I go to a rotation center. Okay, so now your multifunction knobs are controlling what's called beam tilt. It says rotation center, but that's really what this is. So now if I just pick one of the multifunction knobs, okay, watch what happens when I turn it. Okay, so the beam is tilting, but it's not moving. Okay, and that's because I established the pivot points properly. Okay, you can see what's happening to the image, right? As I go way far away from, normal, okay, I end up with a blurry, crappy looking picture, okay? Which brings me to the next point here. So I'm gonna actually show you guys another way to do the rotation center alignment, okay? So the normal way of doing this is, right, I use my focus ring here to turn off the pulsing of the lens. Then if I go clockwise here, okay, it turns it back on. I'm going to spread the beam out so it's outside the flue cam. And this response is, it's not too bad. I'm going to turn this off. You do have the ability here. So sometimes the flue cam, it makes like these on the fly adjustments to its exposure time. And those are usually pretty helpful, but sometimes this ends up defaulting to something a little too slow. So you always have the ability to manually fudge this. So if you uncheck this, I'm going to make this a little faster here. Okay, so now you can kind of see it a little bit cleaner. Usually once you go above 50, it's kind of, the rate is a little too slow kind of to do like normal stuff. I mean, if you put this at like 200, for instance, I mean, you really can't do rotation center with something like that. It's too slow. So anyways, all right. So again, normal way of doing this is you're minimizing the image shifting, okay, while you're with the multifunction knobs. Okay, so you can see here, right, my image is shifting. Now, this can be kind of tricky to do here because we have these kind of long linear features. We can use the fib platinum here. So you can now see it's going kind of side to side, okay? And you're trying to minimize this, okay? So now it's kind of moving up and down, although this is kind of hard to see, right? Because it's moving up and down, but this is kind of in the same direction as these linear features. So this is not, some people can pick this out pretty good. Some people have a lot more trouble. Okay, but that looks pretty good right there. Okay, but I'm going to show you another way to do this. Okay, so let me go ahead. I'm going to turn off the well, actually, yeah, I'm going to turn off the pulsing here. Okay, and now my multifunction knobs are still active, but I'm going to intentionally throw them off. Okay, even though we just set it. Okay, all right. So now I'm going to take the beam, and I'm going to go. Let me switch this back to auto mode. Okay, there we go. And I'm going to go maybe not quite all the way to crossover. Okay, you don't have to go all the way to crossover, but you want to converge the beam fairly small here. And now I'm going to use my focus knob, okay, the inside focus knob, and I'm going to defocus the beam. Okay, so I'm going to go counterclockwise here. Okay, there we go. So I had to change the flue screen view here. Okay, so I changed it from linear to natural. Okay, let me go back here so you can see where I was. Okay, so this is about where I was here. Okay, if I go counterclockwise. All right, so now let me switch this. Maybe it's okay. So yeah, it's easier to see in HDR. Okay, so now what you're seeing here, you're seeing a bright spot, and you're also seeing this kind of diffuse spot as well. But what we can hopefully see here is this is not centered inside this diffuse area. Okay. So to fix the rotation center here, all I need to do, use my multifunctions and get it in the center. Okay, those of you who have done the STEM training will kind of recognize this as very similar to how we do the rotation center in the STEM training. And it is in essence not really any different than that. Okay. So now, and then if I switch to natural, it's a little bit hard to see, but now you can see I have this bright spot centered inside this diffuse area. Okay, and then if I go back, there we go. All right, so now we can actually check this and see how close we were. All right, so a little bit better. Let's see here. All right, so that looks good here. Let me go back and check this out a little bit more here and see. Ah, there we go. Okay. Yeah, so you really, with this, I think the issue here, okay, so yeah, this is actually, I think, a little bit better than it was. So you can kind of take it or leave it, but this is another technique you have to do this here. Okay. So personally, I mean, I don't have trouble doing this with the, just looking at the image, but to each his own. With the stem, it's a little bit easier because your probe is a lot smaller. I mean, we don't really have a probe here. So, all right, let me click done here. Go back to my list here, check this off. Alternative rotation center technique. Okay, all right, next thing, under focus versus over focus. I'm going to increase the mag here. We'll go to 500,000. All right, let me go into diffraction mode and we'll put in an objective aperture. Put in the optimal one for high-res imaging. All right, it looks pretty good. One thing I'd like to point out with the apertures is that when you take them out and you change them, they will go back to the same position that you had them before, but there's always a little bit of hysteresis with that. So I wouldn't just blindly assume when you take them out and put them back in that they're going right back to the same spot. You always want to verify that. So in this case, with the objective, you always have to be in diffraction mode and then, to actually see it. So, but believe me, it's way more reproducible back in the old days when we had to manually, adjust apertures with those, assembly things that stick out on the side. That pain is still fresh in my memory. All right, so let me put this up on acquisition. Take the screen out. Okay. I'm kind of jumping the gun here, but I'll show this to you guys in a second here. All right, so I have a really good sample to demonstrate this next bit here, which is over focus versus under focus. Okay, so in order to determine this, you really need an amorphous signal in your picture. Okay, so we have an amorphous signal from this area here. This is basically amorphized silicon or indium phosphide. And then we also have amorphous signal inside of the platinum. Okay, so in the FFT, as we know, we see these diffuse rings whenever we have an amorphous signal. Okay, but I can use those rings to help me figure out what my focal condition is. And we can see, first of all, right, I don't have this perfectly circular. So let me go ahead and correct that with my objective. Stigmators. Now on my screen, it doesn't look exactly like a circle because of the screen capture that I'm using. It does a little bit of a distortion, so it actually doesn't look quite like that, but there we go. All right, so that's pretty good right there. Okay, all right, so let me turn off this stigmator. None. Okay, so when you're acquiring a high-res image like this, you want to be on the side of under focus. Okay, the way to tell which side of focus you're on versus over or under is how the rings either expand or contract depending on which way you're turning the focus knob. Okay, I can tell right now I'm under focused just by looking at the picture. Okay, but if I want to actually rigorously prove that, okay, I have this diffuse ring, this dark ring right here. Let me turn off the spatial frequency. If I go counterclockwise with the focus knob, okay, meaning I'm weakening the objective lens, I should see this ring get bigger. Okay, so let's see if that's the case, if I'm under focused. Oops, I mean smaller. That's what I meant. Okay, I should see this ring get smaller, okay, when I'm under focused. Yep, and that's what's happening, and I'm actually seeing more rings. Okay. All right, so now if I'm over focused, let me get it to an over focus condition. So if I want to get to an over focus condition, I have to go clockwise with the focus knob until I see that dark ring come back again. Okay, so now I'm in an over focus condition. Okay, I can tell that also by looking at the picture. But if I wasn't sure, again, I could diagnose what's happening based on looking at this first dark ring here. Okay, if it expands and I go counterclockwise, I'm over focused. Okay, so right, because what we did with the under focus was we went counterclockwise and then the rings got smaller. But in this case, I'm going counterclockwise and the rings are actually getting bigger. Okay, so that means I'm over focused, or conversely, I'm going clockwise, meaning I'm strengthening the lens and the rings are getting smaller. Okay, you never want to take an image with over focus condition. Okay, and that has to do with how the objective lens focuses the electrons into the smallest possible area, or the smallest possible point. You always want to be on the side of under focus when you're doing this, and you want to be at what's basically called a small amount of underfocus. And so right here, I'm underfocused right now, okay, but I'm too underfocused. Okay, the way I can tell that is I'm seeing way too many of these dark rings. Okay, usually you only want to see this first dark ring kind of in the FFT, and you kind of want to adjust the focus till it almost kind of vanishes. Okay, right about here. Right, so hopefully everybody can see that. I mean, usually you can tell in the image, but you know, I'll be the first one to say that focusing in TEM is not the most intuitive thing in the world. Unlike, you know, SEM or even STEM, where it is, you know, very intuitive. Okay, but you can see here, if I underfocus a lot, you can kind of see just by looking at the image. I mean, it just looks, you know, a little blurrier. Okay. So again, something like this. So that's the question of how do I know whether I'm over focused or under focused? Okay, so you need to look at the diffuse signal from in the FFT and how the rings change in size depending on which way you turn the focus knob. Let me go back here. Under focus versus over focus. Okay, all right. Next thing we're going to discuss here is rotating the image. Okay, so this is not an SOP, but you do have the ability to rotate the image in TEM mode. Okay, and you can actually do this to any arbitrary angle you want. Okay, but as we're going to see here, when we do this, if we don't do it in multiples of 90 degrees, we end up with our field of view getting cropped. Okay, so right here in the image rotation area of the toolbar, okay, we can put in whatever angle we want here. Okay, so positive would be clockwise rotation, negative is counterclockwise. Okay, these buttons down here go in counter and clockwise rotations of 90 degrees. This guy will zero it out. Okay, so if I do this right here, okay, so 90 degrees increments are easy, okay, because basically you're just rotating the image, right? And so you don't have to change the size of the readout area on the camera in order to accommodate this, okay? But let's say, for instance, that I don't want to go in a nice degree of increment of 90 degrees. Let's say I want to do 37 degrees. What's going to happen? All right, so you can see what happened, and that is that my viewable area got cropped. Okay, so the viewable area actually now is about half, well, actually not about, it is half as wide as it was. Okay, so I think if we, let me put this back to 0. Okay, so if we look at field of view right here, it says 118. Okay, so it's keeping the same. Oh, okay, sorry. No, it did change it. Okay, yeah, so it went from 118 to 59. Yeah, okay, so yep, that is correct. Okay, the reason it's doing this is because you have to remember that your camera sensor is a perfect square. Okay, and so you can't change the actual physical size of your camera sensor, but you can change the number of pixels inside the sensor that are being read out for the image. Okay, so as a result of that, if we're not going in nice 90-degree increments, we end up cropping to just the middle of the sensor. Okay, but we do have the ability, and if we just hold this down, you can see we're going in nice 1/10 of a degree increments. Now, if I wanted to, let's say, for instance, this was the image as we got it, okay, and there's an interface right here. If I wanted this interface to be horizontal, I can use this guy right here. Okay, and that will then automatically figure this out for me. Okay, and then depending on what it is, it's, you know, it's going to crop it down accordingly. All right, if I acquire this, all right, let me go to the processing window. Okay, so now when you acquire it, you're going to see that, now it's 1024 by 1024, whereas, okay, then the full frame, it was, you know, 2048 by 2048. Okay. Now, to confuse matters more, in the thumbnail here, it's showing how it would look with full readout area and 0 rotation. I don't know why it does that, but it does. Okay. So this is an option that you have. The only thing I please ask you to do, okay, make sure when you're done is 0 it out. Okay. Otherwise, the next person is going to be really confused because he's expecting to see this, right? And he ends up, seeing this, and he's going, why does it not look the same way? Okay, so again, make sure you 0 it out if you choose to do that. Let me go back here to the image rotation. Did I not actually put it on here? Oh, there it is. Okay. Okay. Oh, I have it listed twice. All right, well, let me delete it then the second time. Okay, let's talk about some additional ways we can actually collect images. Okay, so in this camera tab right here, we have access to what are called 3 modes here. So we have view mode, which is basically the live mode. And so again, these are the defaults here. So it's reading the full area, but it's reading it at a low pixel density. If I go to acquire mode, it's reading the full area, but with basically 4 times the number of pixels. And then it's using 1 second for the exposure time, and it's doing 1 frame. You are welcome to change this number if you want. Okay, please put it back to 1 second when you are done. Okay, so 1 second is usually fine for this. It usually, with the conditions listed in the SOP, will give you a good signal to noise if you have a sufficiently thin specimen. Okay, but you might want to change this for a variety of reasons. Okay, so those of you who are doing like weak beam dark field, this is in the SOP about why you would change that, because you have a weak signal, so you could increase that. You could also make this number less. Okay, so let's say I wanted to do just 200 milliseconds. Okay. Okay, the advantage of a 200 millisecond exposure is that my image is less susceptible to movement and drift. Okay. Now the converse of that, so let me do a 1 second here. All right, so this is 1 second. This is a second. It's a little bit subtle here, okay, but I can actually see because obviously I'm looking at it, but okay, the signal to noise is much better in the 1 second versus the 0.2 second. Okay, you can actually see the exposure time here in the toolbar. Okay, so your signal to noise is way better when you go higher in time. Okay, the downside of that, of course, is your images get a little more susceptible to drift. Okay, one option that we have to deal with that is to do what's called frame combining with drift correction. Okay, so those are actually 2 different things here. So if we want to look at just first of all frame combining, if we're in acquire mode here, so right now what we're doing is we're acquiring 1 frame over 1 second. Okay, what we can do instead of this, if we want, is we can acquire over 1 second more than 1 frame. Okay, so let's say I change this to 5 frames. What this is doing then is it's subdividing this 1 second into 5.2 second intervals. Okay, and each of those is a frame, and then it's adding them together. Okay, so the net result of that will be like getting a 1 second, 1 frame exposure, but I'm doing it over 5 frames with a smaller exposure time. The reason why you would do that would be to limit the exposure of the camera. Okay, for something like just when you're doing diffraction work, this is where this really shines. I'm not going to go over that in this workshop, but That's where it would really shine. It's not so much useful for doing just regular imaging because we're really not worried about like overexposing the camera, but it would reduce like the total exposure on the camera. So it's safer for the camera. But if we acquire this image now, okay, so this was the frame combined image, and this is the non-frame combined image. You can see they look very good. They look basically the same. It does say 1 second for the exposure time here, just like it does here. Okay, but what's more useful here is to do frame combining with drift correction. Okay, so if we go down to the last tab down here, we get into what's called the series mode. Okay, so basically the only difference between series mode and acquire mode with frame combining, I'm going to put this back obviously to 1 frame 1 second. The only difference here is that when it acquires those frames, it saves them to the file in the processing window. Okay, so if we were acquiring 5 frames, we would actually get all 5 of those frames. Okay, so if we have the settings right here, 100 milliseconds, frame combining, 1 frame. Okay, so maybe calling this frame combining was a little bit of a misnomer. This is a series size, because apparently you can actually put a number of subframes within this. But anyways, we'll leave this at 1 frame. So basically what it's going to do is it's going to collect 10 frames, each of them with a 0.1 second exposure. Okay, so let me go ahead and do this. So we'll click here in a series mode. Okay, so you can see now, so now in your file, you end up with this scrolling bar here. Okay, so you can see, so each of these frames is a 0.1 second exposure. Now what you can hopefully see is these look much poorer in terms of the signal to noise than what I had here. Okay, this is from 1 second, 1 frame, right? Which is as we would expect, okay? But what we can do now is we can frame combine all 10 of these frames, but we can also tell the software to account for movement between the frames. Okay, so once I have this activated, I go to processing, I go to DCFI, which is drift corrected frame integration, and then I have 2 options here. So if this was like a single crystal, we don't really have a single crystal region in here, so I'm just going to do the regular DCFI. We'll see how that works. Okay, so you can see what it did here. Right, so now you can see the frame combined image looks much better, and it looks closer to what we would have gotten from 1 second, 1 frame. But now the advantage of this is that the system will account for movement between the frames, okay? Or at least it should be accounting for movement between the frames. Let me actually, I'm gonna delete this and let me try, I'm gonna try and do it again, but optimize. See, it's got the lattice from the platinum in there, so maybe it's better to do this with the, yeah, so that worked better. Okay, yeah, I can tell by looking at the FFT. Here, actually, let me show you here. So that's a good thing to point out. Let me do this again. DCFI, but regular. Okay, so this is the DCFI with the periodicity. Okay, if you look at the FFT, this is the FFT here. This is the FFT here. You can actually see there's parts of the FFT that kind of get smeared out a little bit, like here and here, that you don't see here. Okay, so that means that the summation was done more effectively here than it would have been for here, which makes sense because you still have lattice detail here. So Okay, so now, right? So now we have a way to do drift correction here for TEM imaging, okay? And so that's what I would recommend here. I would use like 100 milliseconds, okay? And you can make this number, I think you can go up to like 100 frames if you wanted to here, okay? So why would you do something like this? Let's think about, for instance, right? I mean, right now I have a good, a good amount of beam current, but let's say, so let me put the screen back in here. Let's say I'm working with a sample and that sample is very beam sensitive, okay? So let's say I'm going to image it at spot size 7 instead of 3. So how much signal do we have? All right, so we've got only 170 picoamps of current now. Let me just check the alignment here. When you change spot size, usually you should just check all the alignment again. So you can see the C2 aperture's off a little bit. Cutting out on me. Okay, looks pretty good. Beam looks circular, so that's good. But hopefully you know where I'm going with this. So this will give us the ability to do like a long exposure, okay, to get enough signal, but I'm not going to cook the sample, okay? All right, so let me go ahead here, redo the pivot points. Make sure you're grabbing the right knob. All right, looks basically okay. I mean, in principle, the rotation center shouldn't change when you change spot size, but it's, it's a good idea to just check it again anyway. Right, but you can see we have, lost a lot of current. Basically, we've lost 90% of the current that we had before. Let me go put the objective aperture back in. All right, so you can see here, like it's not, it's pretty close, but it's not perfectly centered. So it's pretty good there. So basically we were using 1 second before at spot size 3. So what I'm going to do now is a 10-second exposure. Okay, to try and get the same signal to noise that I was getting before. Now, obviously 10 seconds is a long time for a conventional image in terms of, hoping for it to be stable. Okay, so this is where having the ability to do frame integration and drift correction can be very, very helpful. And you can see actually the amount of current that's actually is less, right? Because we have to spread it out so we get, even illumination. Make sure here. Yeah, it's fine. Trying to make sure those fringes go away. All right, so you can see that's pretty crappy in terms of the signal to noise. All right, so we'll go ahead, get a better focus here. You can increase the exposure time here for the live image just to aid with your, I wouldn't go beyond a second, just gets a little too, but it looks good here. you can actually see there's a little bit of movement going on here, okay? All right, so let's see, 100 milliseconds. And let's see if this will let us go. Okay, so this is gonna let us do a bunch of them. Well, let us do, and we'll do 100 frames. Okay, so 100 frames at 100 milliseconds a frame. All right, so we'll go ahead and do it. And while we're doing it, I will continue to talk to intentionally give it a little movement because it should be able to, you know, obviously account for that. And here we go. All right, so there you can see. Now with this series acquisition, the reason I don't discourage it, but the files in Velox, when you do this, they become very, very large in terms of the amount of space they take up on the hard drive. So you know, it's okay to do this, you know, if you have like a critical image you want, but I wouldn't make a you know, like a regular habit of it necessarily, because we're gonna end up chewing through the hard drive pretty quickly. This is something that we have an issue with a lot on the TEMs, because we do this pretty regularly with like the stem imaging. All right, so we're a little bit more than halfway.
Hey, Nick, while we're waiting, I have a question on the instrument, not about operation.
Okay.
So what is a typical pressure, like vacuum level we have on this instrument?
So you're talking about in like the column area?
Yeah, column area.
Okay, yeah, I can tell you that in a second here.
Mhm.
I mean, I know like it's kind of
Yeah, I remember
erroneous.
it's in log, you have a Pascal reading, I remember.
Yeah, so I mean, normally this is down like around 10 or lower.
Mhm.
We have like a malfunction right now that's
I
preventing
see.
this from getting low. So, I mean, if you put this in terms of a normal number. Okay, so I mean, yeah, normally this is in the low -7 range.
Okay,
So, but I mean, it's
so
still good enough to
okay,
run.
so it's around the -7, 10 to -7 range, right?
Yes. Mhm.
Okay, sounds good. Thank you.
Sure. All right, so let's give this a shot. Now, one thing I'm a little concerned with here, because the signal in each of these frames is so crappy, I don't know how well it's going to do the integration, but we'll give it a try. And looks like it's working pretty well here. So you can see things improve here as it's adding up the frames. Showing anything in the FFT. It's kind of interesting. Anything there? Maybe just wait until it's done. Okay. Yeah, still not a lot here. Yeah, I'm guessing that's an issue with there's just not enough signal still. Now, I mean, the way to get around that, of course, okay, if we wanted to try this, the way to get around this here would be to bump this number up. Okay, so we could bump up this exposure time per frame. Okay, so if we went to 200 milliseconds, the other thing you could do too, if you reduce this, you know, this binning down to something lower. I mean, if we put this at, say, let's do 1/4 of a second. Okay, and then let's see here. We'll do 40 frames. And we'll see if that maybe helps us a little bit more. Okay, so you can already see the difference here. Yeah, I think like even, you know, you have to make sure at least within each individual frame, you got something, you know, to work with. If you have to, if the overall signal per frame is just too low, then it's just not going to work well. Okay, so yeah, this should probably work a little bit better. All right. Let's see what we get now. Yeah, I can already tell it's looking a lot better. Yeah, and over like a quarter of a second, that should be, you know, quick enough that you're really not going to see much of an effect from, you can see it kind of fouled up there. What happened? Let me try that again. Maybe it was something I did. Oh yeah, so you can kind of see, you can see it in the FFT when you're seeing this kind of rippling stuff. Yeah, that's not good. That means it's not aligning the frames properly. Why is it doing that? Interesting. I mean, the final signal to noise looks, you know, reasonable, but all right, let me try it one more time here. Let me try it with regular DCFI because it just, maybe that'll work better because the signal's not as high here. Yeah, see, it's still smearing out. Interesting. So you're right about, then you can take this and actually you can cycle it through and you can see the effect. It should anyway. Why is it not doing it? Okay, yeah, you can see. So you can actually see at what point, you know, your summation starts to kind of go awry. Yeah, see right there, it's still. Huh, interesting. Yeah, so that didn't quite work as well. I know this would work. I know this will work fine. I mean, if we put it back to the high current situation. So this is 1 second. I mean, if we try this a little bit more, but then if we go more than that, we're kind of, you know, getting to the point where it kind of defeats the purpose. And this is an auto stop. All right, let me stop this. Put the screen back in. Yeah, image processing, you know, drift correction, stuff like that, that always works better the more signal you have in your individual, you know, frames. So because I mean, if you don't have enough, you know, the system is effectively trying to like add noise, and it just doesn't do that very good. All right, so I'm gonna be quick and dirty here and just realign the C2 aperture, but I'm gonna leave everything else as is. All right, looks good. All right, so we're back to spot size 3. All right, so let me go back here to this guy now. And let's bump this down. And we'll go 20 frames. So that would be like 2 seconds. And we'll see what we get now. All right, let's try it again. Yeah, so it's looking good now. Yep, so. Yeah, so it worked fine. I mean, obviously, you know, like most things work better when, you know, there's a lot of signal. I mean, the one thing you can kind of see here in the FFT, you can kind of see around the edges here, there's a little bit of this kind of patchiness. That is from the alignment process of the frames. But what you don't see here is like the diffuse signal doesn't have like chunks of it kind of missing. So that's good. That means the summation or the alignment of the frames was correct. Okay. All right, so that's the frame integration. Let me put this back here. All right, so that kind of gives us a good segue here. All right, so we've got a really nice area of the sample here to do two things, okay? Focus and to correct objective astigmatism, okay? But what if we're on an area of the sample that we don't have this luxury, okay? What can we do? So what I'm talking about here is the rest of this sample is, you know, a big single crystal. Okay, so let me take this out here. And actually, you know what I'm going to do? I am going to, that's the top of the sample. I'm going to mark this position here. And you're going to see why here in a minute. We're going to call this, we'll call this PT. So you can actually mark positions within the sample too. If you're working on like a lamella like this. Okay, so there's that, the active layer. Trying to find an area I can remember this corner here. Perfect. All right, so I am going to do a zone axis alignment here. One thing you can do as well, and this is helpful when you're trying to see like how well you're aligned with the zone axis, you can actually change the scale here on the flu cam. Okay, so you can change this to any of these other ones. So you change it to temperature, right? Sometimes this is easier to see. So you can kind of see like these green spots. We're not kind of perfectly centered here, right? So that means we're still maybe a little bit off the zone axis. Okay, so this is a little closer. I'm nudging the alpha tilt, but you can see now that's a little bit better than where it was. Okay. All right, so because I tilted, I'm going to go back and I'm going to make sure I have eucentric height reestablished, push eucentric focus. Okay, so that's worse. There we go. Check one more time here. All right, it looks temperature. All right, so now we're probably off a little bit the other way. So this is common. There we go. So it's just pretty close. All right, let me put in my objective aperture. All right, that looks good. All right, so I'm gonna go back up to 500,000, which we were using for the imaging. So this area, obviously this was made by FIB, and obviously it has a damage layer, but as you're gonna see here, I really don't have a very strong amorphous signal here. Okay, so the question is, like, how am I gonna focus properly? Right? So, I mean, one way you can do this to get yourself close to the focus. So the focusing can be kind of tricky here, okay, because you don't have any amorphous signal and you can't really rely on the FFT. What you can do then, if you converge the beam down, okay, so you have it inside the viewable area, okay, what you're looking for here is what's called delocalization. So you can see, like, outside the beam here, I'm getting this stuff, okay. If you minimize that, so you're right about, and then if I go, it comes back, okay. So right about here in the middle, that would be about neutral in terms of the, so right about there, okay. So this would kind of be my middle point, and then from here, if you could go backwards, kind of counterclockwise slightly with the focus to get you to an under focus condition, okay. So this would be how you'd have to kind of dial in the focus. So if we put this up on, and this is better to do actually on the flu cam. Whoops, wrong one. Okay, but you can see, right? I mean, I really don't have, there's a little bit of an amorphous signal there, but it's really not very strong. Okay, so, I mean, from here, and even though I'm bumping up the exposure time here, it's still really not helping me a whole lot, okay? I mean, if I look really closely, I can kind of see like a ring there, but it's not terribly close, okay? So that's why you can get it. Now I am making some changes here to the focus knob, okay? And you can actually kind of see that faint ring in the middle there, kind of changing size, right? So this is actually pretty close here. So I'm going to take this image. Yep, there we go. Looks good. Okay, but that's how you would get your image focus in the ballpark, right? So you'd have to use the flu screen, okay, converge the whole beam down, and then minimize the image delocalization, right? So you can actually see it here. Okay, right about in here. And then from here, you can make small changes, okay, by actually looking at the image, okay, on the camera itself, right? So again, if we go backwards here, right, so we can see, but you know, relying on the FFT here becomes not very practical. Okay, same idea as with the astigmatism, right? So the astigmatism correction now is, you know, more or less impossible. I just don't have enough of an amorphous signal. Okay, so this is where I can correct it at a different place initially, right? So I already corrected it over at the platinum, and then I came over, okay? If I hadn't done that before, right? So I can actually, let me mark the stage position again. All right, let me drive to the platinum here, see how well this works. Now, if I do this, it's going to change the stage tilts, I think. All right, so I'm not going to do that. What I'm actually going to do is I stored this position. So I'm actually just going to drive straight north here till I get to the top of the sample, because I know that's where I have that amorphous layer and the platinum. But that's the point, is you know, if I wanted to correct that, I've got to find something that's amorphous to do it. It's really not possible conveniently anyway to do it otherwise. I suppose if we got really tired of this, we could just put the because the stage movement is kind of coupled to the mag. So when the mag is really low, okay, I can tell we're getting close though. There we go, we're getting close. There we go, okay. All right, there we go. Okay, so once you find something amorphous, right, there you go, okay? You can make your correction here, okay? And then just move back to where you were before. And now if you store the stage position, I mean, we already corrected it, it looks good, okay? But obviously you can't correct it just, I mean, if we move on to this, right, this is all crystalline. And again, you know, I'm getting very little distinct amorphous signal there in the FFT, okay? But if I move over here, okay, this works great for that. All right, so now, once I've, you know, tweaked this, I can drive back and hopefully this works pretty good. It may not be perfect. Oh, it actually went pretty close, strangely enough. Huh, look at that. Now there may be a difference in terms of the focal conditions between the two, you know, points, because there might be a little bit of a height difference. So it's probably a good idea to, yeah, so there was. Right, so it's actually not too bad. Yep, so it looks good right there. And I already knew my astigmatism was good, but let me try doing a series acquisition here and see. All right, let me blank the beam. All right, so now this one's got a lot of crystalline signal and single crystal signal. So this is really designed for this guy. So we'll see how well this works. So far, so good. Yeah. Okay, so it looks good. Again, this stuff here you're seeing, that's an artifact of the frame alignment. Okay, but yeah, so it looks good otherwise. The spots are nice and, you know, symmetrical. I don't see any like dip in the intensity around here. And then when you zoom in, you know, it looks great. So okay, so moral of the story, like with most things TEM related, is it gets better when you have more signal. All right, so let me go ahead here. Check these off. Okay, I kind of briefly touched on this earlier, which was how to pick this exposure time. Again, so, you know, in the SOP, and we're assuming we're doing one frame here. So again, in the SOP, you know, regular conventional imaging, whether that's bright field or high res, if you have a sufficiently thick sample or thin sample, I should say, then this should be plenty. 1 second. But I mean, you do have the you can go up or down from this. Again, I probably wouldn't go up, because again, you're going to be more susceptible to things like instability in the picture and drift. So that's when it becomes a little more relevant to do like the drift corrected frame integration. What you have to be kind of careful of or cognizant of, and generally this isn't an issue with just conventional imaging, is that you don't saturate the camera. So that's why using 1 second is good, because even if you put the whole beam on the camera, we know at those conditions, it's not going to cause a problem. Okay. All right. So the other thing I wanted to do then, let me stop that. Put the screen in. All right. So those of you who screen is blanked. Why is my screen blanked? Or beam blanked? Okay. Those of you who do diffraction work with the flu cam. Okay, so I'm going to show you another trick here, and this particularly those of you who are doing single crystal diffraction work. So generally speaking, if you're working with a single crystal and you want to do diffraction work with the flu screen, or even not with the flu screen, you're doing it with the SATA camera, which I'm not going to go over here today. Generally, you're trying to get like a really good zone axis alignment when you collect the pattern. Okay, so if we go ahead here into diffraction mode. Okay, insert the objective. So what I'm doing now is I'm making sure I have a parallel beam. Okay, check the aperture edge. There it's blurry. There it's nice and sharp, so I'm good. Okay, and then using my intensity knob to focus the spots. And now I have a parallel beam. Okay, I'm not going to mess with my intensity knob again. All right, so this this layer right here, let's say I want to isolate the pattern from this layer. Okay, so we'll use an SA aperture. So I already did, as you saw before, like a coarse zone axis alignment. Move that guy to the center. Go into diffraction mode. So now we'll see. And then this is where we want to see if temperature. Wow, so this actually looks really good here in terms of the zone axis alignment. Okay, so that's no fun for what I was trying to do. What I wanted to show actually was, all right, so I'm going to take the joystick here and I'm just going to move around until maybe I don't have quite perfect zone axis alignment. I could always do it by fudging with the tilts, but okay, so here I can actually tell. I can tell I don't have perfect zone axis alignment. Okay, this is my direct beam right here, and you can see like this beam is a lot brighter. Okay, so in principle, I shouldn't have that. I should have like uniform intensity of the spots around the pattern. Okay, and actually, I'm going to fudge with the stage tilt here slightly just to kind of, drive the point home. Okay, so you can see right here, right? I clearly don't have good zone axis alignment. Okay, now you could, okay, you could very meticulously fudge with your stage tilts here to try and get that spot to zone axis alignment. Okay, but if you just want to get a zone axis pattern for the purposes of acquiring the diffraction pattern, we can do a trick by adjusting the beam tilt just to get a good zone axis alignment just for purposes of acquiring the pattern. Okay, so the way we do this is we go to the dark field tab. Well, actually, we don't have to go to this tab. We just want to, okay, so on the, we're going to have to go back to it later though. On your right-hand panel, there's a button that says dark field. And then if you push it, now your multi-functions control the tilt of the beam. Okay, so now we can use the tilt of the beam to give us a diffraction pattern that has a good zone axis alignment. Okay, obviously, those of you who are doing things like you're working on not single crystals, particles, right? You could do this with your particles as well. Okay, right, so you can see here, I'm making it worse, right? I'm seeing a Lowy circle here. Okay, there's my direct spot right there. Now the pattern is going to shift when you do this, so I'm going to go over how to get around that. If you get lost, back you click on dark field, click reset 0, 0. Okay, there's your direct beam right there. All right, so now we're getting, there we go. So now we're getting warmer. Okay, so you can actually see, right now this guy is the brightest, and I have everything around it is kind of uniform. Okay, so now this is actually a good zone axis alignment. Okay, so if we go actually, all right, let me add this. Okay, so I'm going to add. Now watch, I'm going to go back. That's where I was. Okay. Okay, and that's right. Hopefully you can all see the difference. Okay. All right, so now when I'm taking the pattern, switch this to grayscale. I put the beam stop in. All right, so now my beam stop isn't centered here. Okay, I want the beam stop, or I want the direct beam under the stop. Okay, so but my multifunctions, they're now set to beam tilt. So what am I supposed to do here? Okay, what you can do here, if you right click, you can change these to beam shift, or sorry, diffraction shift, not beam shift, diffraction shift. Okay, and then you can shift the pattern back without changing the tilt you just did to the beam. Right, switch to natural mode, and now I have a nice zone axis diffraction pattern, and I can do an acquire here of this, and there we go. Okay, but again, so I wouldn't do this. So this is fine to do this for purposes of getting alignment to get a zone axis diffraction pattern. Okay, this is not something that you want to do to get zone axis alignment to try and then go image the sample. Okay, the reason for that is now I've deviated my beam from the optic axis of my objective lens, and now I'm going to have way more aberrations in my image than I would before. Okay, we kind of actually saw that when I was going over the rotation center, and we saw how the image looked kind of really crappy when I tilted the beam really far away from, you know, how it was supposed to be, right? So effectively, I'm doing the exact same thing here. Okay, but here I'm not doing it for the purpose of getting a better image. I'm doing it just to try and, you know, align along the zone axis, because the zone axis wasn't perfectly aligned with the incident beam to begin with. So I sort of, you know, reversed the process and I tilted the beam to go along the zone axis. Okay, if that makes any sense. All right. Obviously, if you're going to do this, please, you know, you can reset this. So all you have to do is click reset 0, 0 when this is done. Okay, you can delete all of these, and then on your, and we can see here pretty clearly now, right, the difference. Okay, this is not as good of a zone axis alignment as it was. Okay, and then on your right hand panel, you want to uncheck dark field. So, and then it goes back to diffraction shift. All right, let me go back to image mode. And there we go. Okay, I think that's actually close to everything on my list. Yes, I think it was. The only other last thing, which is kind of a housekeeping thing, I don't know if any of you have kind of so maybe you've seen like some other microscopes, FEI microscopes, other facilities, or maybe you've seen other videos or SOPs. One thing I'd like to point out is that these tabs here in microscope control, these are, you know, purely arbitrary in terms of how they're named. Okay, so you have the ability, and please don't do this, I'm just showing you how to do it, but you could name these anything you want. Okay, so these weren't, a lot of these weren't the default names. Okay, so I actually I tried to name them logically. Okay, but you could name this, for instance, if you wanted. Come on. Okay, ketchup, right? Mustard. Pickles. Okay, again, so these are purely arbitrary names that go up here. Okay, so these are something you could, you know, again, if you're the person overseeing the microscope, and the same thing with these now I can't rename these panels. Okay, the panels are fixed to be what they are, but I can actually control which panels go into which of these tabs. So you might see on a different microscope, for instance, you might see something else. So we do have, thankfully, a lot of flexibility with how you set up the user interface here, which is nice. Okay, startup alignment. Oops, actually alignments was what it was. All right, so, and that was basically what I wanted to cover. Are there any questions from the 2 people left?
I had a different question.
A different question. Okay, go right ahead.
Is there a way to change the alpha beta tilts manually by entering numbers or something instead of pressing that control panel?
Okay, that's a great question. You do have the ability to do that with the alpha tilt. I do know that for sure. So right here, you can set this number to whatever you want. Right, so, you know, you want to put in 5.3. Okay, that will do that. But yeah, as far as I know, there is not a way to do this with the beta tilt.
Okay, thank you.
Yeah, you're welcome. I mean, you can obviously manually adjust it, and then you can, like, if you look on the, you know, you can right down here, right? You can just adjust it till you get it to some number, but there isn't an input dialog box. Anything else?
I'm good.
All right. Well, I will, once this is done, I will get it up on YouTube, and those of you who maybe found it useful can revisit it again later. So thank you for stopping by, and I will look forward to seeing you all again soon.